I'm very happy to be able to welcome Brad Chamberlain. Brad is a master engineer for Hewlett-Packard Enterprise, formerly Cray Incorporated, but sometimes both now these days. He's the technical lead for design and development of the Chapel parallel programming language, and he was also a founding member of the Chapel project. Brad earned his PhD in computer science and engineering from University of Washington in 2001, and he currently is still associated with the department there as an affiliate professor of the Paul G. Allen School. And with that, Brad, I'll hand it off to you.
Great. Okay, thanks very much. And I'd like to thank the organizers for inviting me to give this keynote. I give a lot of talks about Chapel, obviously, but nobody's ever really asked me to talk about how we compile Chapel. And that's, of course, a topic really near and dear to our hearts. And PACT seems like a great place to talk about that. So I'm excited to have this opportunity and got to make a lot of new content for it. So the title of my talk is Compiling Chapel, Keys to Making Parallel Programming Productive at Scale. And I'll talk more about what this title means in the next couple of slides. Let me just get my focus right. Okay, so if you're not already familiar with Chapel, Chapel is a parallel programming language that we designed and developed at Cray and now at HPE. Chapel is designed to be portable and scalable. So I can run Chapel on my laptop. I can take it to a commodity cluster, to the cloud, or to a supercomputer, and sort of run the same program in any of those settings. And it's also an open source project and a collaborative project. So we do all of our development work at GitHub, and we have code contributions from members of academia, industry, and labs. If I were to summarize the two main goals of Chapel at a high level, the first is to support general parallel programming, which you can think of as if you have some parallel algorithm in your mind and some parallel hardware you'd like to run it on, you ought to be able to do that in Chapel. And if not, we're not achieving that goal. And the second one is to make parallel programming at large scales far more productive than it is today. And this term productive is kind of a loaded term. If you talk to 10 people about it, you might get several different definitions as to what productivity means to those people. So I'm going to take a moment and just sort of talk about what productivity means to maybe some different personas, if you want to think about it that way. And I feel like when I talk to either recent graduates or current students, to them what feels productive is something similar to what they are used to using in school. And for a lot of people these days, that's Python, maybe depending on what field you're in, something like MATLAB or R, maybe Java if you're coming up in computer science, or maybe something else. But there are a lot of modern languages out there, and yet in HPC, the languages we use are still older ones, I would say. Now, if you talk to seasoned HPC programmers, they'll say that productivity is that sugary stuff, which I can't really afford to use because I need full control in order to ensure good performance. And the idea here is, my institution has spent all this money on this supercomputer. I need to make sure to take best advantage of that. And I have this attitude that productivity is going to be counter to performance. And while there are many instances of productive language features in the past that have been counter to performance, we don't think those two things are necessarily in opposition to one another. And then in fact, well-designed productive features can actually improve performance. And I'll have some examples of that today. And then if we talk to computational scientists, they say, what I really care about is thinking about my science, my ideas, and being able to express those as best possible without having to wrestle with a lot of architecture-specific details. Like, that's not what I'm interested in. That's not where my expertise is. That's not why I publish papers. And so my team's response to what productivity means to us is kind of a blend of these three things. We're trying to design a language that lets the computational scientists express what they want without taking away that control that HPC programmers require, all implemented in a language that is attractive to a recent graduate. So a lot of times when we talk to people about the fact that we're creating a language, there's sort of this reaction of surprise or disdain. Getting a new language implemented and adopted is obviously a huge effort. It's both a huge technical effort, but there's also a huge social component to it as well. You're trying to convince people to use this language, when they maybe have something that they are used to and it's more adopted. So why are we doing a language? I think the short answer is we think that parallel programmers deserve better. If you look at the state of the art in high performance computing today, it's kind of this big mishmash of libraries, pragmas, and extensions. And it allows people to get great work done and do great science on these large systems. But for the programmer, I would say it's a pretty painful experience compared to kind of mainstream modern programming languages, let's say. And the second part of this is that we think that parallelism and locality are sort of two core concerns for scalable parallel computing that are things that deserve first-class language features and not just to be kind of bolted on or tacked on or added later on. So by designing a new language, we can promote those to first-class concepts. This isn't just an attitude of our team. This is a slide from a keynote that Kathy Yellick gave at our annual Chapel workshop a couple of years ago. And her title of her talk was called "Why Languages Matter More Than Ever," sort of alluding to the fact that with exascale coming along, languages can really be a big boon. And in her talk, she argued that languages can provide new syntax, semantics, performance optimization opportunities for compilers, and new algorithmic creativity. And that's a message that really resonates with me and with my team and says a lot about why we're pursuing Chapel. And frankly, the last thing here is that existing languages don't really meet our desires. They're good at some things, but not others, and they don't sort of have the right blend of things that we're looking for in a language. So to be more specific, we're trying to create a language that is as programmable as Python. So has that same kind of easy to read, easy to write code nature that people are used to in Python. But where Python takes a big hit in terms of performance because it's an interpreted language, it has a global lock, we want to sort of blend the programmability of Python with sort of the goodness that we're used to in HPC. So we want a language that's going to be as fast as Fortran in terms of the scalar code, that can scale to the largest machine scales, as well as MPI or SHMEM or UPC, which is how people program these large systems today. That's as portable as C, a language where you can feel like you can run it anywhere. As flexible as C++ in the sense of being able to create your own types and sort of extend the language from within the language. And then this last one sometimes gets a smirk, but we want to create a language that's as fun as your favorite programming language. And the idea here is a lot of us get into programming because we find programming really, really fun. And while HPC computing is very fun, it's fun to run on these large scales and run really fast. Frankly, the programming is something that I think most people just grit their teeth and get through. So we'd like to return that sense of fun to HPC programming. So as I said at the outset, this is pretty different than my typical Chapel talk. Most of my Chapel talks, I sort of summarize Chapel's features and accomplishments, and my goal is to sort of grow the community, get more people invested in Chapel and its mind share. In this talk, I'm going to do a little bit of that, but I'm going to spend a lot more time than I normally get to talking about Chapel's compilation and optimizations in the compiler, which of course is an appropriate topic for the PACT audience. And the overall thesis of this talk is that if you design a language well, you can both improve user productivity and help the compiler out, make the compiler's job easier and help it do great things for you. All right, so with that, this is the outline of my talk. I've just given you a little bit of context and motivation for Chapel and for this talk. The meat of my talk will be these next two sections. I'll start out by talking about some of Chapel's features and how we compile them. You can think of this as the nuts and bolts of Chapel. What does it take to just get Chapel up and running? And then the next section will be about some optimizations in Chapel. I'll call out a couple of interesting optimizations that leverage unique features about the language. So you can think of this as sort of bells and whistles, sort of nice things that a compiler can give you. And then I'll end with a quick summary and some resources. Before I go on, let me just check and make sure that we're not having any technical difficulties. I don't know if Jeff or one of the other mods can just sort of make sure everything's going smoothly.
Everything seems to be going well.
Great, thanks very much. All right, so let me go on. As I said, this next section is going to be introducing some key Chapel features and giving you some insights as to how we compile them. Again, sort of what does it take to get Chapel up and running? All right, whenever I talk about Chapel, I use this little stack of sort of feature areas as a roadmap. I sort of think of the language features as falling into these 5 rough categories. And I'm going to start today by talking about what I call lower level Chapel. I put lower level in quotes because it's still pretty high level compared to what most of us use in HPC. And I'll start specifically with the base language, which is like the serial core of the language. Or if you took Chapel and removed all features related to parallelism and locality, the base language is what you would be left with. And I'm going to do this through a simple computation. This is a Fibonacci iteration. And each of the samples I'll show you in this part of the talk is a complete Chapel program. You could put this into your favorite editor, compile it, and run it without any changes. And this one's just going to print out Fibonacci numbers, basically. This code relies heavily on using an iterator. If you're younger than me, you've probably used languages with iterators before. If you're of my generation, they may still seem new and strange to you. So just to describe them really quickly, this loop here for f in fib of n is basically calling this iterator, which looks a lot like a subroutine or a procedure in any other language. And that subroutine is basically going to drive that loop. But unlike a typical function, these iterators contain yield statements, and the yield basically passes a value back and binds it to the index variable of the loop, f in this case. And then we execute the body of the loop for that yielded value. And here's a little thing that says that. We execute the loop for that value. Then once we've executed that copy of the loop, we're going to go back and continue the iterator from where we left off, yielding additional values, running the loop again, until eventually we fall out of the iterator or explicitly return from it. And then here, what I'm showing is just a compilation of this program. Our compiler is called CHPL. So we compile the program and then run it. And here I'm running it for a problem size of 20. So I would see the first 20 Fibonacci numbers print out. So again, this is a fairly simple introduction to some of Chapel's features. I'll mention that in the early years of Chapel, when I would give this talk, this is the sort of thing that would cause some HPC programmers to say, you know what, I'm not using those iterators. Like, that's just not something I have ever used or need. And I think there's a little bit of fear about the performance as well. And to me, that's kind of ridiculous. It's sort of like saying, I don't believe in code reuse, or I don't believe in parameterizing my code, or I don't use subroutines in straight line code. Because if you think about these iterators, they're exactly the same kind of mechanism as a procedure or function is for just normal straight line code, but in loop context. And they can make a very complicated loop pattern much simpler to read in the same way. And they can do it without incurring performance overhead, which is what I'll show you next. So let's look at how we implement this iterator and this serial loop over it. So focusing in on that loop, the first thing we're going to do is rewrite the loop by taking the iterator body and inlining it. So you can see that most of the code here is just the same code as my fib iterator on the left, and I've bound that argument x to the value n, since that's what I'm passing in as the actual argument. And then the next thing we have to do is take this yield statement, and what we're going to do is essentially inline the body of the loop back into that yield. And so you can see I've put the right line here, and again, I'm binding current, which is what I'm yielding, to f, which is the name of my index variable. And by doing those two simple transformations, I've essentially ended up with something that's kind of pretty close to C code, except for this iteration of the range, but you can imagine how that would be a C loop quite easily. And so I've taken this nice high-level abstraction and reduced it to something that really shouldn't scare anyone in terms of performance. And as a result of this, you can get these iterators to run just as fast as if you weren't to use them and just put the code in yourself. But again, with the benefits of code reuse and parameterization. Now, this is a fairly simple case, but lots and lots of cases are this simple in practice. A couple more advanced cases I'm not going to talk about today are zippered iteration, when you're iterating over multiple iterators simultaneously in lockstep, and recursive iterators, which obviously are harder to inline. But that's what I wanted to tell you about the base language and implementing it. I just want to note before going on, the base language is kind of huge. Like, we could spend a full day talking about base language features and how we compile them. Because to be a modern language and to be adopted, you need things like object-oriented programming and generic programming and error handling, compile time metaprogramming, and so on and so forth. And so I would just want to say that Chapel has all those things, but I won't be talking about those today because they're not the things that make Chapel unique. So instead, let's go on to some things that do make Chapel unique. Staying at this low level, I'm going to talk about task parallelism, how we express running things in parallel, and locality control, how we talk about where things ought to run. And before I go on, I'm just going to introduce one term that's key for this talk. So hopefully everyone will get it before we go on. We have this notion in the language of what we call a locale. A locale is a part of the system that you're running on that can run tasks and store variables. So you can think of it as it has processors and it has memory. And on most parallel systems, you can think of a locale as being a compute node, right? So if you're on a 1,000 node cray, that is 1,000 locales essentially. And whenever you run a Chapel program, you specify the number of locales you want to use on the command line. So here, for example, I'm saying, let's run my Chapel program on 4 locales. And within my program, I'll end up with an array of these locale values that represent those compute resources on which I'm running. And the one other thing you need to know before we go on is that when you start running a user program, that code is going to start running on locale 0. So your main procedure, if you will start running on locale 0. All right, so let's look at a simple example. This is essentially a task parallel hello world. I'm going to create a bunch of tasks, and they're each going to print a little unique hello message identifying themselves. And just call out a few features here. You can see that I'm referring to this built-in identifier here. This is a way of referring to the locale on which you're currently running. So wherever you are on the system, here refers to that compute node. And you can make queries about it, such as how many processing units does it have, which you can think of as being a core essentially, right? How many cores do I have? And here I'm going to bind that to this constant num tasks. You can also ask things like, what's my locale's name? Tell me the host name, essentially, of this compute node. So that's a way of introspecting about the system we're running on from within the language. That it supports a really clean way to kind of talk about things like how much memory do I have, or what kind of resources do I have. Next, we're going to use this COFORALL loop to actually create our tasks. This is a lot like the for loop we saw in the previous example, but the COFORALL essentially says this is a concurrent parallel loop, and each iteration of the loop should execute as an independent task. So if I were running on a 4-core system, num tasks is 4, I've got 4 trips of this loop, and each of those trips is going to be a completely independent task running asynchronously from the others. So here's another example of me compiling this program and running it. I've created these 4 tasks. They're running on this node called N1032. And you can see that I haven't done anything to synchronize or coordinate between the tasks. So these messages might get printed out in any order, just depending on how the tasks happen to be scheduled by the runtime. And here you can see it's a slight permutation on 1, 2, 3, 4. All right, so far what I've shown you, this is just a shared memory program. If I was running this on my 1000 node Cray, it would never actually use any resources other than locale 0. And the reason is I haven't done anything in this program to refer to those other locales either explicitly or implicitly. So let's look at what we would have to change in this code in order to change it from a shared memory code into a distributed memory code. And essentially what I'm going to do is just introduce another level of parallelism here, another outer COFORALL loop to introduce some more parallelism across my compute nodes. So what I'm doing here is iterating over that locales array I mentioned earlier. Again, this stores an array of locale values representing the compute resources I'm running on. And it says create a task for each one of those locales. So if I'm running on 16 nodes, I'll have an array of 16 values. This loop will have 16 trips, and each one of those trips will be its own task. So the next thing I want to do is say each task should go run on the locale that it corresponds to. And at this point, I have what you might think of as SPMD parallelism, where each compute node is essentially running one task. And from there, I'm just going to do the same computation before, where each task is going to query the number of cores on its local node, create that many tasks locally, and print out the messages. Right? So I'm just using the same COFORALL concept as before to create more tasks, and then the on clause to say where those tasks should run. So here I'm running that on, say, a 4 locale run. And so if I, again, assume I've got 4 cores per node, I'm going to have 16 messages printed out. And you see that now I've got sort of, multiple 1 through 4s and also multiple different node IDs being printed out in my program now. All right, so let's look at how we implement, let's look at this inner COFORALL loop and how we implement that. The first thing we're going to do is outline the loop body. And by outline here, I mean the opposite of inline, create a procedure out of the loop body. So you can see I've taken that write-f and put it into this function, and I've passed in this arg bundle, which refers to outer scope variables that I'm referring to. In this case, I'm going to use that to get at my task ID, TID, and the num tasks value, both of which came from outside the COFORALL loop. Then I'm going to take the COFORALL itself and rewrite that as a serial for loop. So I basically change it from a COFORALL to a for loop. And then within that for loop, I'm going to capture some variables. And I'll talk more about how we do that in a few slides. And then create a task pointing it to this outlined procedure as the code it should run, and these captured variables as the arguments that it should use. And this create task is essentially a call down into our runtime, which can create that using a lightweight tasking layer like qthreads or a pthread per task, or however you want to map it down to the system. All right, so that's how we implement COFORALL loops. Let's also look at how we implement on clauses. They're actually a little bit more interesting. So again, we're going to basically take the on clause and take its body and outline that into a function. In this case, I'm not actually referring to any non-local variables. So I pass in arg bundle, but I actually don't refer to it in this code. And then we're going to rewrite the on clause itself as an active message. An active message is basically a style of communication in which you say, hey, you node over there, I want you to run such and such a procedure for me with such and such arguments. And so you can see, again, I'm capturing some variables, and then I'm calling into the runtime, basically saying, run on this locale, using this function I've created over here, and these arguments that I've bundled up for you. All right, so both the COFORALLs and the on clauses are fairly simple rewrites in the compiler. And the biggest element of both is this variable capture. So let's talk a little bit about that some more. And I'm going to extend my example somewhat. The previous one didn't actually refer to any outer scope variables. So let's actually create some outer scope variables to make this a little bit more interesting. So I'm creating 3 variables here at the program scope, 2 bools, verbose and done, and an integer total. And again, my program starts running on locale 0, so these variables will be allocated on locale 0. So next I'm going to use an on clause to migrate my computation over to locale1. I'm going to do some, it's a little bit of a bogus computation here, but basically, you know, check if we're done or not, print something out if we're in verbose mode, and add something into the total. So conceptually what I'm doing is migrating my original task over to locale1, but the data remains where it was on locale0. So what I need to do is give locale1 the ability to refer to those data values back on locale0. And I'm going to put those into this argument bundle we've been seeing in the code. So the compiler starts by saying, well, which outer scope variables are referenced within this on clause? And it sees that done, verbose, and total are, all three of them in this case. And then it goes through these variables and decides how it's going to bundle them into the argument. It's going to put some representation of all three into the argument bundle. And the first it's going to say is which of these things are constant? Because if they're constant, we can just capture those by value. And so you can see my verbose is declared as a constant at the top of the code here. So that's a value I can just snapshot and put into my argument bundle. And then we look at our memory consistency model and say, which of these values does the memory consistency model say it's safe to cache? And we'll capture any of those by value. And the memory consistency model says that done is safe to cache because it's a read-only variable within this on clause. And we can see that there's no synchronization events requiring us to go back and refer to the original. So we're also going to snapshot that into the argument bundle, but for different reasons than verbose. And then finally, any other variables, we're essentially going to capture what we call a wide reference, a pointer back to where that variable lived on locale0. And that way the new locale can refer to the variable using RDMA to access it, basically remote puts and gets to read and write it. So having done all that, we can now pass the argument bundle off to locale1, and it can refer to done, verbose, and total in order to get back at those original variables that it needs to. So again, I think this is a fairly straightforward transformation, but one that's really, really powerful. If you compare this to how most people program HPC, I'm basically referring to variables no matter where they live on the system, if I can see them in my lexical scope, just like in any other programming language. And this is what is most natural to programmers. And in fact, when they start using Chapel, they almost don't realize how great this is. But if you compare this to like SPMD programming, where you typically only have sort of a view of what you own locally, and you have to explicitly communicate to get at other nodes' values, this is the kind of thing that makes parallel programmers much more productive. All right, so there are other task parallel features as well we won't get to today. I'm just going to flip past this. All these slides will be available afterwards if you want to look through them in more detail. All right, so let's pop up to the high-level features in Chapel. And the main one here is data parallelism, and we'll talk a little bit about domain maps as well, which are kind of how we get data parallelism within Chapel. And again, I'm going to do this through a really simple example. This program is essentially a program that's just going to declare a two-dimensional array and fill it up with some arbitrary values in parallel. So again, kind of artificial, but a good example to illustrate how compilation works here. And again, there are a couple new concepts you need to know about. The first is in this line, I'm declaring what's called a domain. Domain in Chapel is essentially a language concept that represents a first-class set of indices. And here I'm declaring the domain to have the set of indices 1 to n, 1 to n. So I end up with this two-dimensional index space, which I've shown in the picture here. And it looks a lot like an array, and it is a lot like an array, except that rather than storing data for each of those indices, it's really just the indices themselves. So you can think of it as like the size and shape of an array or an iteration space, if you will. The next thing I'm going to do is declare an array over that domain. So I declare this array A. I say it's declared over all of the indices in D, and I'm going to store a real floating point value for each of those indices. So now I've got a two-dimensional n squared array A of floating point values. And again, I've used the domain to do that. And then the last thing I'm going to do is use this for all loop to iterate over the indices in the domain and assign the elements of the array a basic function of their indices I and j. And here I've used a for all loop, which is the third loop type we've seen today. So we saw the for loop that's serial, the COFORALL that literally uses a task for every iteration. And this for all you can think of as being kind of somewhere between those two. It's typically going to not use a task per iteration because, like in this case, we're iterating of these million indices. Creating a million tasks to do this very simple computation is probably going to be overkill. We'll spend more time creating and destroying tasks than actually doing work. So typically for alls, we'll use the amount of hardware parallelism that's available. So if I'm like running on a 4-core laptop, this for all loop will typically decompose those million iterations across those 4 cores and give them each a quarter of the work. So if I compile and run this program and I run it for a small problem size just so that the output makes sense, I end up with this little two-dimensional array of values, again, as a function of the indices. All right, so far, oh, I just noticed I put the wrong values in one of these two places. I'm not sure which one. All right, so again, this is a shared memory program. Nothing in my program here refers to remote locales either explicitly or implicitly. So if I ran this again on 1,000 nodes, this is only ever going to use the memory and the resources of locale 0 because I haven't done anything to say otherwise. So again, let's look at how we can take this simple program and change it into a distributed memory program. And again, it's a fairly simple transformation. I'm essentially going to add 2 lines of code here. And what these do is essentially say, how should I map this domain and the array and loop over it down to the system? And I'm using the cyclic distribution specifically. So essentially what I'm doing is, the cyclic is what we call a domain map. And it says, how do I implement this domain's indices and the array elements and the loop's iterations over D down to the program's locales? How do I map this computation to the system, essentially? And so in the upper right here, you can see sort of a color-coded map. Let's say I'm running on 4 locales. What the cyclic distribution is going to do is distribute in a cyclic manner the indices of D and the elements of A across those locales, so that now my for all loop is going to use all of the cores on all of the compute nodes on which my program is running. So again, a fairly simple change to the code, but a fairly dramatic effect in terms of taking it from a shared memory code into a distributed memory code. And most importantly, I want to point out, this only required really changing the declaration of that one domain, and then all of the other computation could remain unchanged. And this is a really powerful feature when you're developing on your laptop, but then deploying on a supercomputer. All right, so here's the run I showed before where I was just running on a single locale. If I add on a num locales equals 4 flag, I'm now going to run on 4 locales. The output's going to be the same because I haven't done anything in the program that's dependent on the locale values or identities. But of course, if I run this on a large problem size, it ought to go 4 times faster now because I'm using 4 times as many compute nodes. All right, so that's how we do data parallelism in Chapel, again, for a very simple example, both in shared and distributed memory. Let's look at how we implement data parallelism. And I'm just going to zoom in on kind of the key lines here in order to get myself some more screen space. All right, so all these data parallel features are lowered basically to method calls on these domain map objects. So cyclic is an example of the first domain map object we've got here. And so if I look at how I'd rewrite this code, essentially what we do is just rewrite sort of this high-level Chapel syntax into basically just sort of object-oriented method calls and things. So I'm going to create a new instance of the cyclic distribution corresponding to my dmapped clause over here. I'm then going to use that cyclic distribution and say, create a new domain for me. Let's call that D. And then I ask that domain, please create a new array for me and call that A. So these factory methods are basically how we build up the arrays and domains that implement the Chapel program. And then the for all loop is interesting. Basically what we're going to do there is we're iterating over D. So we basically ask D, hey, there's a for all loop here. We'd like to invoke your default parallel iterator. And we're going to implement this a lot like the previous for loops we saw, where we just inline that default parallel iterator and then inline the loop body back into it again. Now the iterator itself and all these domain map objects and methods are basically implemented in Chapel using the lower level features we've already seen. So they're implemented using objects and methods and tasks and on clauses. And just to give you an example of that, let's look at what this default parallel iterator looks like for a typical distribution. I've got a typo here. This should say iter instead of proc because it's an iterator. But basically inside of the cyclic domains parallel iterator, we're going to see a pattern much like what we saw earlier in the talk. We're going to create a task per locale, move those tasks to their respective locales, create a task per core, and then compute as a function of our locale and task ID which indices we own of this domain. And then basically just iterate through those serially and yield them back. And again, we're going to actually implement this in practice by inlining this iterator that the user wrote into the for all loop, or now it's a for loop. And then the parallelism is all within the iterator. And then we'll inline the loop body back into where the yield statement was. All right. So what I want to emphasize here is that all this high-level data parallelism is essentially implemented, not baked into the compiler, not baked into the language, but as user-level code in Chapel. So things like this cyclic distribution or block distribution is all basically Chapel code that you can go and look at, and you as a user can write your own distribution. It's not, I'm not going to say it's straightforward, but it's possible. You can write your own classes that expose the required interface and then distribute or lay out your arrays and domains in any manner that makes sense for your computation. And the compiler is just going to rewrite down to those methods you've created. And it's a really great system. All right, so as with the other features in the language, there are other data parallel features we're not going to see today. Basically, all the kinds of things you want to do with arrays and parallelism. I'll just mention that in addition to the dense multi-dimensional arrays we saw so far, Chapel also has strided arrays, sparse arrays, and associative arrays. So a fairly rich set of data types that you can do data parallel computations on. All right, and with that, I'd like to turn from kind of the basics of Chapel's features and how we implement them into the optimizations, a couple of optimizations that are enabled by the language and how we implement those in the compiler. And I'm going to do these in the context of a couple of very simple benchmarks. The first one is stream triad. And I should say that I picked these simple benchmarks just because I think it's easiest for a talk to get your head around. But these optimizations also apply to patterns that commonly show up in much larger and more interesting codes as well. So this first benchmark we're going to look at is stream triad. If you're not familiar with it, looking at the picture is probably the easiest way to understand it. We're basically going to take a vector C, multiply all its elements by a scalar alpha, add that to another vector B, and assign to a third vector A. And as probably most of you know, this is sort of trivially parallelizable. If I decompose my vectors across my compute nodes, shown in red here, and then parallelize each of those chunks across the cores within the compute node, I can basically do a pleasingly parallel computation in which nobody has to really communicate with anybody else other than kind of startup and tear down, essentially. Oops, I keep losing my focus, sorry. So if we look at the reference version of stream triad in C and MPI and OpenMP, the code looks something like this. I've highlighted the MPI code in red, and there's not much of it here because there's not much communication. So this is basically just kind of the startup and tear down for MPI. And then the OpenMP, I've tagged a couple of loops as being parallel so they can get multi-core parallelism in blue. And then the main computation itself is this green loop down here at the bottom that does the actual vector computation. And the rest of the black is just kind of boilerplate C to allocate the arrays and initialize them, things like that. Now, this is a code that you actually know enough about Chapel now that most of you could probably write this yourself. This is stream triad in Chapel. As you can see, it's much kind of shorter and sweeter. Again, part of that is because it's a modern language and we've learned a lot from other modern languages. And part of that is because by building parallelism and locality into the language, you can express parallel patterns much more succinctly. So, we're going to declare a distributed domain here, our 3 arrays over the domain, initialize those arrays, and then do A equals B plus alpha times C. And that's our computation. Now, having short codes is nice, but of course in HPC, if they don't perform well, then nobody's going to really care. So happily, this is a case where Chapel competes basically neck and neck with the reference version. This is a scale or a performance graph. So higher is better. And the x-axis is the number of locales or compute nodes we're running on. So out here at the end, we're on 9K cores. And I've plotted 3 lines here, the reference version in green, and then 2 different Chapel versions in blue. And you can see they're all essentially on top of each other. They're all maxing out the memory bandwidth and taking full advantage of the system as you'd expect. So again, not just a short code, but also a very efficient code in Chapel. All right, there's another way that you could write stream, and this is motivating the optimization I want to talk about here, which is rather than writing this A equals B plus alpha times C, I could write it more like my previous data parallel loop I showed you. I could use a for all loop and say, for all I in DOME, do A sub I equals B sub I plus alpha times C sub I. And this is a completely valid, different style of writing the computation. And for things that actually care about what the value of I is, sometimes it's necessary. But what we were finding was that this version ran about half as slow as the previous one I showed you. And let me tell you about why. So these array accesses here are basically accessing into this block distributed array. And if you look at what the random access method for a block distributed array looks like, essentially there's a lot of logic in here because we basically have to say, well, is this index one that we own locally on our locale? If so, we can just do a normal kind of offset computation to decide where that lives in memory and yield that, or sorry, return that value back. But if some other locale owns it, then we have to figure out, well, which locale is it that owns that? And then we have to do a bunch of computation and communication to refer to where is that address on that remote locale, and let's pass that back instead. And a straightforward compiler without any optimizations like I showed you so far would basically just translate these array accesses down to this routine. But as humans, we know, of course, that all of these array accesses are well aligned and there's no communication required. So they're always going to be in that local case. So we're basically paying a lot of overhead, mostly in terms of the conditional, which of course thwarts compilation and optimization. And we're losing performance as a result of it. Okay, so as a programmer, if you know this, you could rewrite this by explicitly saying these are local accesses. And this would get you back to the original performance again. But of course, this is annoying. Nobody wants to go through their code and say, is this local or remote? It's anti-productive, which is of course what Chapel's all about. So this is the optimization that we've implemented to deal with this issue. When the compiler looks at this code, it knows that DOM is the domain of A, B, and C. And when it looks at the loop, it knows that the index I is an index from DOM. So it knows that I is basically an inbound access of A, B, and C. And more than that, it knows that whichever task owns iteration I also stores the local values of A, B, and C corresponding to I locally. So the compiler can essentially look at this and say, oh, I can trivially see that all of these are going to be local. And therefore, it can strength reduce the loop to the more lengthy version that you could write as a programmer. All right, so this is an optimization that I'm a little bit embarrassed to say. When we created the Chapel language, this is a big part of why we put domains and arrays in the language as first-class features. And this was motivated by work on ZPL that my group did at UW in the 1990s. But it was only implemented this past summer. So it's kind of been sitting waiting for someone to get to it. And my colleague Engen finally got to it this past summer, which is great. This example I've shown you is fairly straightforward. I just want to call out that Engen's also extended this to a lot of other kind of much less obvious variations, where he's used kind of the algebra that we support on domains and arrays to make a stronger determinations of like, oh, I can tell that this index I is local, so let me use a local access for that array access. And this just shows kind of the before and after. So this dark blue line is where we were with this random access version prior to this optimization, and the light blue shows after the optimization. And this light blue line is basically tracking those same reference versions I showed earlier, where all the lines were superimposed. All right, so at this point, basically, we can write stream in this whole array fashion, in a zibbered fashion I didn't really talk about today, or in this random access fashion, and those will all get identical performance as you'd hope. So you can choose whichever style best suits your computation. All right, I'm going to move on to my second optimization for today and switch to a different benchmark. This is the HPC Challenge Random Access Benchmark. If you're not familiar with it, essentially you have a distributed table across all of your compute nodes. And then all of your tasks are essentially just making random updates to that table as fast as possible to random locations. So this is sort of the opposite of stream, kind of like if you had completely unstructured random access across the whole system memory, what would the performance be like? And this is the reference version. Again, the MPI code is called out in red. And you can see there's a lot more of it here. And that's not too surprising because this is obviously a much more communication intensive benchmark. So we have to spend a lot more code coordinating and communicating with one another. This is the comment at the very top of the MPI code. And it essentially says, these 3 columns of what's pretty unreadable to most of us is essentially just doing a bunch of random updates to this table. And what's telling is that this is that kernel computation in Chapel. And you can see that it's about as short as the comment itself, right? So we're saying for all updates that we have to do and values in this random stream, take that random value and update the random table element by that random value. Okay, so again, another case of very short, very compact code that's, I think, much clearer, much more readable to understand what's going on. And I'll show you the performance we had with this code a couple of years ago. Again, the reference version is in green here, and the Chapel version for a couple of subsequent releases are in blue. And we were pretty happy with these results because not only were we competing with the reference version as we scaled out, but in fact, we were beating it as the machine scale got higher and higher. And so we were feeling pretty good about this, but as we dug into it more, we found there was a lot more we could do to optimize it. So that's the next optimization I'm going to be telling you about. So the key here is that we're going to basically lower this loop to loop a lot like the ones we've seen before. A COFORALL across all the locales, so we create a task per locale, a COFORALL across all the cores within the locale, and then a serial loop that sort of iterates over all of the iterations that that task owns, where in the interior of that loop, we're going to be doing these random table updates that we need to do. And so the observation here that allowed us to enable this optimization is, the user has basically specified this computation as a for all loop that says there are no data dependencies between these operations. But then the innermost computation here is basically a serial loop that's doing an XOR. And because this is RA, it's a random remote XOR. So basically I'm saying, well, let me go XOR that thing over there. And now I'll wait for that to finish. And then that'll come back. And now let me XOR that thing over there. And I'll wait for that to finish. And it seems kind of ridiculous to serialize these given that we're in the context of a parallel loop. And so that's kind of the key insight for this optimization. And what we realized was, there's nothing about this XOR operation that anything else in the loop body is dependent on. So we don't really need to wait for it to come back. We can kind of fire that off and then go on to the next one immediately. And so what the compiler does now is it looks for cases like this where the last statement in a parallel loop can be basically fired and forgotten about temporarily. And it sort of rewrites operations like this XOR into what we call an unordered XOR, which is like an asynchronous XOR. And then at the end of the serial loop, we do this fence to make sure that all of those have now completed before we go on. So now rather than waiting for each of those computations before I go on to the next one, I'm just firing them all off as fast as I can, driving the network as hard as possible. And then only after I've done all of the ones that I own, waiting before going on. Okay. And again, this is something that's sort of uniquely, I think, made possible by this for all loop, which says, hey, all of these iterations are independent. And that gives the compiler a lot of semantic leverage to take advantage of when optimizing the code. So what we found here, sorry, I should say, this was implemented by Michael Ferguson and Elliot Ronahan last year. So what I want to show is this is the performance we got as a result of this. This green line that's down near the x-axis is the exact same reference line I showed you a couple of graphs ago. I've dropped the historical numbers on our part. And this dark blue line is the chapel performance we get as a result of this optimization. So again, by introducing that additional asynchrony, we could drive the network much harder and make the performance go much, much faster. All right, so again, a case where the chapel code is fairly short and sweet and readable. The reference code is, I would say, much less so. And of course, a user could expend more effort and end up with an implementation like the chapel implementation. We typically compile down to C. You could write the exact same C that we generate. It's just a question of, well, how much effort is that for you and how much more code would you have to write and how portable would it be? So the other thing you might think is, well, maybe a compiler could do this in MPI, but I think if you look at this page of code and think about what would it take for a compiler to reason about what this code is doing and come up with that same optimization, I mean, to me, this is sort of like, it's not even worth trying. And I would say the reason is that MPI is all about specifying specific mechanisms, do this buffering, do this communication, and less about the intent of the code. Whereas chapel is focused more on the intent. Let's do all these parallel updates in parallel with some specification of how it should be done as well, but through better abstractions like domain maps, for example, rather than explicitly specifying it all. All right. We've looked at a couple of examples today of a couple different computational patterns and benchmarks and optimizations. We could talk hours about different benchmarks and our speed on them. I'll just say that we look at a lot of different computations in HPC and sort of key benchmarks and patterns. And in general, for the ones we've studied, we end up with versions that compete with or beat the reference versions. But I'm running out of time, and mostly I just kind of want to make this high-level point that benchmarking is really important and a key activity for my group. But at the end of the day, what really matters is, are people actually liking what you're doing and benefiting from it? Do the end users care? So what I want to do before I wrap up is just call out 6 notable applications of chapel out in the field today. Some of these are in academia, some are in the government, some are in industry. The first couple up here are kind of what you might think of as traditional HPC computations. So physical simulations of the universe in one case, or computational fluid dynamics in the other. And then these bottom ones are all what you might call sort of more data science-y or AI kinds of things. We've got some branch and bound optimization going on. This great Arcuda project that basically gives you NumPy within Python, but underneath the covers it's running on Chapel, and so you can run on these terabyte-sized arrays running on your Cray in real time as you're interacting with it in your Jupyter notebook. A hypergraph library developed at PNNL. And then within Hewlett-Packard, we are developing AI technologies using Chapel, such as hyperparameter optimization and feature selection. And there's obviously not time today to talk about each of these projects, but I want to say that when we talk to these users about what they value about Chapel, it's a lot of these same things that led us to create the language. The code's fairly easy to read and write and reason about. The performance is good. It scales up from laptops to supercomputers. It's portable. So that's been really great to corroborate our message. And we've gotten a ton of great feedback from these users to improve the language and improve its performance, including some of the optimizations we saw today. All right, so let me wrap up quickly and then leave some time for some questions. To summarize my talk, I hope what I've shown you today is that Chapel is a language that cleanly and orthogonally expresses parallelism and locality, which again, I would argue are the 2 key things to worry about or think about in scalable parallel programming. And in addition, it also gives us ways of talking about how to map the computations down to the system, either at a low level using these on clauses and locales, or using higher level abstractions like these domain maps, which specify how to map entire computations down to locale sets. A lot of times when you live in the HPC community, anytime anyone talks about a language like Chapel, they use the term, magic compilers or heroic compilation or things like this. And to me, these are just sort of really dismissive and kind of degrading terms. I hope what I've shown you today is that nothing about Chapel is particularly magical or heroic. The language defines quite explicitly sort of how things are mapped down to the system and how you as a user can control that mapping through things like domain maps, for example. I hope you've seen that the lower level features have a fairly straightforward compilation path, which is essentially a rewrite with a little bit of traditional compiler analysis about where things define, where they used, how do they cross scopes, things like that. And the higher level features, as we saw, are all built within the language on top of the lower level features. So those, again, are primarily a rewriting step. But at the same time, as you've seen, we've designed the language with parallel optimization in mind. So things like these for all loops and these domains and arrays give the compiler rich semantic information that you can use to tune for locality and to introduce additional asynchrony. I hope you've seen that Chapel is powerful. The code ends up being fairly succinct and straightforward. And as we've seen in the few examples today, it can result in performance that competes with or beats conventional programming in C, MPI, and OpenMP. And if we think back to the original slide I showed from Kathy Yellick's talk, we've seen examples today about how Chapel's syntax, its semantics, enable cleaner code and enable new performance optimizations. And though we haven't talked about it, I think also sort of enable users to be more creative in their algorithms and to change their code more easily. Finally, I'll just kind of assert through our users that Chapel's attractive to computational scientists and Python programmers. Now, the organizers asked me to talk about challenges and next steps, so I want to talk about a couple of those. One of the big things we don't support today is compiling Chapel down to GPUs. You can use GPUs from within a Chapel program by interoperating with them, writing your code in CUDA or whatever. But really what we want to do is map Chapel's arrays and for all loops and things like that directly down to the GPU. So there are questions here about how will the compiler need to evolve and will we need to change anything about the language to support these? A second feature going on is to re-architect the compiler. This started out as a research project and our code base bears a lot of the marks of that. It's not always as clean or lovely or fast as it ought to be. And so we've gotten to a point where we really need to go back and basically take a lot of cruft out of the compiler and make it more production worthy. Part of that's going to be reducing the compilation times, which are pretty slow today, either through separate compilation or incremental recompilation, as well as just making things better. And we also hope to introduce an interpreted or interactive Chapel programming mode where you could be in your Jupyter notebook writing Chapel code line by line rather than going through the compile cycle. We're always going to be continuing to optimize the performance. There's always more to do there. We're also working on releasing Chapel 2.0, which is essentially a version of language in the future which will guarantee backwards compatibility for the core language and library so that users don't have their code break with each release. And we're always trying to grow the Chapel community, both in terms of users, but also in terms of developers of Chapel. And speaking of growing the community, I want to mention before wrapping up, we are hiring. I think we've got one position open currently, but I expect that if everything goes as anticipated, I think we'll be opening 5 or 6 full-time positions this coming year. So keep an eye on our job site, and I need to actually update it. I just learned about the current open position yesterday. And if you're not looking for a full-time job, we also have internships in the summer, and we've hosted Google Summer of Code students for the past several years. And so those are other ways to get involved in the project as a paid member of the team. Oops. This slide has a bunch of resources, our homepage, social media, and different ways of interacting with the community or getting support. Again, don't feel the need to jot these down. All these slides will be available afterwards. And I've got some suggested reading here as well. Some are high level, kind of talking about the project or language as a whole. Others go into some of those high level features for data parallelism in a lot more detail if you want to learn more about how we do those. So just to wrap up and to come back to my thesis statement, I believe strongly that well-designed languages can improve user productivity while also enabling new compiler optimizations. And our team believes that Chapel is such a language. So that's my talk, and it looks like I uncharacteristically left a few minutes for questions. So let's see what we've got in the Q&A box here.
Yeah, that's certainly okay. Thank you, Brad. That was a great talk.
Thanks.
So we have a couple questions, and I'll, if you don't mind, I'll read them out, and you can answer them, so you can kind of focus on just answering the questions.
Okay.
So we have one from Rich Fudig at Georgia Tech, and he asked a question that I also had was wondering about. You know, you talked about slides 68 to 71, that it took about 20 plus years to get this optimization to map the local accesses automatically via the compiler.
Right.
His question is, was this just a fluke, or is it a fundamental issue with new languages and compilers?
Yeah. I really like that question. You probably saw me giggling as I was sort of embarrassedly talking about how long it's taken us to pull that together. I would say that this is a result of Chapel's a really, really aggressive language. Like, you know, you saw sort of the tip of the iceberg today, but on a bunch of my slides, I sort of pointed out all these other features we have. And a lot of people at the beginning said, well, you're never going to succeed with all those features. But we sort of said we're never going to succeed without them, because if you've got a language that only does one thing well, but isn't general purpose and doesn't have everything people want from a modern language, it's not going to succeed. So it's essentially taken us a long time to get the core of the language implemented and sort of all of the key features working correctly. And then even once we got to that point, we had users who were like, you know what, I care about performance, but what I really need is error handling. You don't have error handling yet, please add that. Or you don't have good memory management of classes, please add that. And so sort of the priority all along has been to get the breadth of the language implemented and working well, and sort of taking care of users that were features that were actually preventing users from getting work done. And as a result of that, a lot of the optimization work that we had imagined doing right off the bat at the beginning of the project ended up getting pushed way out. And it's kind of a chicken and egg problem, because if you don't have the features, people aren't going to use it. But if you don't have the performance, people aren't going to use it either. And we're sort of finally hitting the point in the project where we've got both the features and the performance, and have really started getting more traction last year or two. So like those 6 projects I mentioned, most of those are kind of new as of the last 12 to 24 months, I would say.
Great. So it's it only takes 20 years to get an optimized language, in other words.
Right.
Great. Okay, we have kind of two questions that I think are very similar, from Vivek Sarkar at Georgia Tech, and then we also have a very similar question from Janil Gandhi. Both of them said, "Great talk," and I think you know, the question is, what do you see as the challenges and opportunities for Chapel as we enter an era of extreme heterogeneity? And that could include things like GPUs, but also TPUs, and you know, maybe even something even more, you know, stranger, like a FPGA or a domain-specific accelerator.
Right. Yeah. So this is, of course, the $1 million question, and it's one I think as a community we've been wrestling with and trying to answer for 10 or 15 years. And I'll say that kind of a next step on my slide. I don't want to imply we've never done anything with GPUs. We have worked on targeting Chapel to GPUs and more exotic architectures over the years, but traditionally more in a research mode and often in collaborations. Currently, we've got one going with Georgia Tech, actually, and in the past we've had them with UIUC and AMD. And I think there are 2 main challenges there as I view it. The first one is just the problem of code generation. So with the diversity of architectures and accelerators that are coming online, the question of how to generate code for those and sort of maintain your portability is kind of a big engineering challenge. How do you structure a compiler to do that as best possible? And I'll say that our sort of approach there is that we have an LLVM backend, and LLVM, I think, as this community probably knows, is increasingly becoming sort of the compiler to invest in and build on, essentially. So our hope is that by going to LLVM's IR, that'll give us a less painful way of generating code for a diversity of architectures. But that's kind of what I view as the #1 challenge that lies ahead of us. The second one is kind of talking about, like, should this run on the CPU or the GPU or the FPGA or whatever, or which memory type should this be allocated in? And there, what we've got is an experimental concept with the language that, again, hasn't received a lot of weight, but it exists on master today. You can use it, which is this notion of what we call a hierarchical locale. And so where the locales, as I've talked to you about them today, I've just said, think of that as a compute node. We have the ability within the language to create locales within locales. So you could sort of say, this is my CPU sublocale, this is my GPU sublocale, or this is my high bandwidth memory sublocale. And in the same way that you could use on clauses to say run on this node or that node, you could say run this on the GPU or store this in the high bandwidth memory or things like that. Now, I think this is an important tool, but I don't think it's a panacea. There are significant challenges still, like how much does this hurt the programmer having to put these on clauses in saying where everything runs, and to what extent can we wrap that into our domain map story to kind of abstract these details away from the typical programmer. In addition, I think there's sort of this compiler challenge of like, if you can't statically know whether your on clause refers to one type of resource or the other, are you basically compiling tons and tons of code clones just in case I happen to run this on the GPU or the CPU or stored in this memory or that memory? So I think there's significant challenges ahead there, but I would also say that these are challenges all of us are facing as a community. And I think a language like Chapel that has this very kind of layered approach of lower level task parallelism and locality, and then higher level data parallel abstraction on top of it, and the ability to extend those abstractions within the language. And in fact, these locale models can be defined within the language too. I think it's a much better starting point than kind of doing it all from scratch. So I'll stop there for that question.
Looking forward to hearing more about the hierarchical locales. That seems really interesting.
Yeah.
So this, I guess we have two more questions. We'll see if we can squeeze them in here. We have Michael Merrill ask, based on the recent work with the projects, how do users feel about your multi-resolution approach to the language?
So Mike Merrill is one of our users. We should turn the question on him. But I would say from what I've seen, I think people generally like it. And I guess the way I'd put it is, I think people find it really reassuring in Chapel that like you can write these high-level loops and distribute arrays and things like that. But then there are ways when something fails you, either the compiler has a bug or isn't getting the performance you need or something like that. There's sort of alternatives to drop down to lower, more manual levels, whether that's the task parallelism locality control within Chapel, or in some cases, calling outside of Chapel to C or something like that. And I think to a lot of people, that gives them some confidence that if we just said, your program has to all be Chapel and you're stuck with us, that would terrify people essentially. And we've had people do some pretty heroic things in terms of, we weren't at a state where they could get where they wanted. So they basically were able to drill down and get closer and closer to the machine and ultimately get what they wanted. Now in doing so, they lost some of the benefits of the language and maybe some of the portability because maybe they've bound things more closely to their system. But again, that's the programmer's choice. So they were able to do that.
Yeah, that's a gotcha from one of your users. Okay, we have one more question, and then we'll get you off the hot seat. So it says traditional languages are such as C++ are evolving. Some programmers would like to think as in a higher level language like Chapel, but write approximately equivalent code in a traditional language like C++. Do you see Chapel-like high-level parallelism features being integrated in traditional languages like C++ in the future?
Yeah, so I think that it's definitely the case that we will see traditional languages have more and more of these capabilities, whether in the language themselves or whether through some sort of standard library like Cocos or something like that. And I think that's all well and good. Like, I don't consider that sort of scary or competition. And people often ask us, like, why didn't you just create a C++ template library rather than a new language? And for me, what I think it all comes down to is, while you can create, for example, C++ libraries that have a lot of these same capabilities of Chapel, at the end of the day, when you look at the code, what you see is lots and lots and lots of method calls and parentheses. And frankly, I mean, that has the benefit of it keeps the language simpler, it keeps the compiler writer's job simpler, but it also makes the code much, much harder to look at and reason about. I would say definitely for a human programmer, but to an extent also for the compiler. Like if everything looks like a method call, it's much harder to reason about the semantics of things. And so by elevating things like domains and arrays into the language in Chapel, we first of all give the user much nicer syntax for dealing with those things other than sort of like .slice_my_array, .index_my_array, things like that. But we also give the compiler, again, this rich semantic knowledge that we've talked about that allows it to do optimizations that, again, if you didn't just do a template library, if you put that into C++ proper, the compiler could also optimize. But, it's an effort and it'll take a while to get there. And frankly, I don't think at the end of the day, it'll look nearly as clean just because that's the way I feel about C++ code.
Right.
So that's my answer to that question.
Okay. Thank you very much. We have one more question. We'll take that one offline,
okay,
just so we can move on. But thank you very much, Brad. Unfortunately, we need to get a virtual audience applause to thank you. But thank you on behalf of all the attendees. we'll move. There's one more C++ question that is probably a longer discussion, and we'll move that offline to the Hoover chat or somewhere else. So.
Great. Thanks again for having me. I appreciate it.